All right, welcome back, everybody. Just a couple of things that I want to make sure to say to everybody today, and then you'll have some time to work on your homework and also on finishing your extra credit challenges. So first off, if you have not taken your quick quiz yet, please go ahead and do that right now, and pause the video. Okay, if you've already done that. Just a couple of announcements that were posted, but I want to make sure get to everybody. First off, if you weren't there for day 2 last week, the recording is posted. You can see that link here on the announcements. The other announcement, very important, is we're going to be picking up chem kits, or we're going to be receiving chem kits. You guys are going to be bringing those back in. You need to do a couple of things. First off, I need you to at least bring back 2 things. So that's the model kit and the scale, right? Those 2 things, please put them back in the bag. Put your name on the bag, put my name on the bag so we can know whose class you're in and all that. And then return those back to the school. If you have the batteries, the thermometer, the funnel, and the ruler, we would appreciate those back as well, but we really need those model kits and the scales back. That's very important. If you aren't coming to school right now, we have 2 pickups. We're going to be picking up on Tuesday and Thursday, 3 to 4:30. Okay. You can also bring it other times, but that'll be the specific time that we're looking for them to come in. Hopefully you can bring them in during that time period. If you are coming to school, just bring it when you come to school next class period, and I can take them from you. Okay. Today, I'm going to briefly go through a few notes with you, not a lot here. And then, like I said, you'll be working on some homework related to this and some extra credit challenges, finishing up those extra credit challenges. All right. So, first off, we're going to start with something that is called a heating curve. Okay. Now, that's a very misleading name because it's not very curvy, but it can be a little bit curvy in actuality. In theory, it's a very straightforward, straight lines everywhere, but in reality, it does get a little bit more curvy than this. But anyway, the important thing to note about a heating curve is that when you warm something up, like a solid, when you warm that solid up, you're going to see that it is going to stop changing temperature even though you keep adding heat. And that's a little bit strange to see. But, of course, just because you're adding heat does not mean you are changing the kinetic energy of the molecules. You might be, but you might also be changing their potential energy, right? Those are 2 different things, of course, that you could be changing the energy of. So if you're changing the potential energy, you won't see the kinetic energy change for a while. So that's what you see from B to C. The ice is melting, the potential energy of the molecules is changing, but the molecules themselves are not actually changing their speeds very much. Then when they go from liquid to gas, right, from D to E on this graph, again, you're going to see that it takes a long time for the temperature to change. It's just going to essentially stay flat. So this is why when you cook things in boiling water, you can count on the water to be one particular temperature the entire time, right? It stays at 100 degrees Celsius the entire time it boils. So this is very useful for cooking, of course, right? It helps you to control things. Anyway, so again, you see the same sort of feature, right? Again, you're pulling the molecules apart. Now, one thing you might notice is that D to E is a much longer line segment than B to C. That means that it takes a lot more energy to completely pull molecules apart and to turn them into gases, right? Which actually makes sense. And this is true for any substance, basically, that the heat of vaporization, which is effectively what that is, right, is far larger than the heat of fusion, the melting amount of heat. Anyway, so that's a heating curve, just something to note. We also want to talk about vapor pressure, and vapor pressure is the pressure that is generated when molecules of a liquid escape into the gas phase. So those molecules escape into the gas phase are going to, of course, cause, they're going to cause collisions, right, with whatever container they might be in. And at some point, they actually equilibrate to where there's only a certain number of molecules that would be in the gas phase over a liquid, if it's contained, that is, right? If you had an open container, obviously they would just keep on escaping, and that's why a glass of water sitting on a table is eventually going to disappear, right? You're not going to have any water left, right, over a long period of time. But if it was contained, only a certain number would get into the gas phase, and then it would stop. But that would be essentially your vapor pressure. Now, we've seen a graph like the one you're seeing here, where it's called a Boltzmann distribution, where at lower temperature, the molecules are mostly going slow, right? And at higher temperature, they're kind of more spread out. Some are going faster, some are going still slow, but a lot of them kind of in the middle. But what you'll notice is that in the higher temperature gas, right, there are more molecules which are going to cross that threshold into being able to escape into the gas phase, right? They have enough speed, enough energy to escape out from the liquid. And so the higher the temperature is, the higher the vapor pressure is going to be. And we should know this already. I mean, if you think about it, if you're smelling food and it's fairly cold food, you're not going to smell it very strongly, right? But if you start to heat it up, put it in the microwave for a little bit, or put it in, the oven for a little bit, and then you take a whiff, right? You're going to start to notice that there's stronger and stronger smells, right? So as the temperature increases, the vapor pressure is increasing, and you can tell that. Now, vapor pressure for different things is quite different, right? So different substances are going to have different vapor pressures at a given temperature. So you might see in this graph on the right that the vapor pressure of diethyl ether is quite high at 20 degrees Celsius, right? It's like 450, almost 500 torr at 20 degrees Celsius, whereas ethyl alcohol and water much, much lower at 20 degrees Celsius, right? So that's telling you something. That's telling you that diethyl ether has far weaker intermolecular forces, because remember, I told you that vapor pressure is the only one of these physical properties that it gets smaller as the intermolecular forces increase. So ethanol and water have not just dipole-dipole, but they have hydrogen bonding, right? Diethyl ether only has dipole-dipole forces, and that's why ethyl alcohol and water are so much lower in vapor pressure at the same temperature. Okay, one other thing I should mention here, and that's boiling point. Almost everybody mischaracterizes boiling point. Boiling point is not the temperature at which something boils, even though that sounds like it would be straightforward. Boiling point is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. Okay, it's the temperature at which a liquid's vapor pressure equals atmospheric pressure. Now, that's actually kind of an important distinction, because if you're at normal, right, atmospheric pressure, 1 atmosphere, 760 torr, well, then boiling point is, the expected, or, at least for water, it's the expected 100 degrees Celsius, right? But what if you don't live at sea level, right? What if you live a little higher up, right? We currently live only a little bit higher up, but let's say you lived in the mountains. Well, now your pressure outside, your atmospheric pressure, is going to be considerably lower, and that means that the boiling point of water is lower as well, okay? And that's why if you go up into the mountains, the temperature of boiling water is just not as high, and therefore when you go to cook things, if you try to cook them in boiling water, like spaghetti or something, put it in boiling water, it's going to take considerably longer to cook, okay? So that's kind of a good thing to know, of course, all right? On the other hand, vapor pressure can be helpful in cooking faster if you can control the atmospheric pressure, right? If you can increase the atmospheric pressure. How do you do that? Well, you do that with a pressure cooker, right? So a pressure cooker can be used to, hold in the gases to nearly double atmospheric pressure, at which point that means, like going back to this, right? If we had double atmospheric pressure and you extrapolate that blue line, right, you could see that our boiling point is going to go up quite a bit. In fact, if in most pressure cookers, you can get the temperature up to something like 130 degrees Celsius, somewhere in that range. And that has a very dramatic impact on how long it takes to cook. It really lessens the time it takes to cook, right? So anyway, I think that's something to think about, right? Why do you think this happens? I'll leave that to you to consider. All right. That's all I have for you for notes. I do want you to check online to your extra credit challenge submissions. I have put comments on them. If you don't see comments, please do email me. It may be that something got crossed or, whatever. Anyway, signals got crossed or something. But just let me know if you don't see them. You might only have one person in the group with comments. All right. That's just the nature of the thing, right? But, so look on all people's in your group's submissions just to make sure that I did mark one of them. And I do want you to take a little time. Your proctor should allow you to get into groups to start discussing this and start working on your identification of your compound. Otherwise, also check on your homework. So if you're not working on the extra credit challenge, then you can just start working on the homework that's assigned. All right. If you have any questions for me, please do send me an email. I will be checking my email, and I'll see you all